Hello, my name is Pablo Gil, and I'm professor at University of Alicante in Spain. I'm going to share my work that I've been doing on manipulation over the last 3 years. More specifically, I'm going to present some strategies of tactile perception, which are based on deep learning methodology to try to achieve a stable grip. Okay, the manipulation of deformable objects presents very much challenge, mostly visual sensor, where used versus other kind of the sensors. Some of them can be the modeling of the deformation to achieve desired shapes from initial shapes. This requires that we determine grasping points on the surface and manipulation movements for a robot. This one can plan movements to get a desired shape and control the deformations, but also will require to determine forces to be applied by the robot. The perception of contact between surfaces, objects, when the object which is being grasped is another application. It is very necessary to achieve stable grasping and prevent the object slipping from robot. Visually, the contact perception can obtain from intersections between region of hand and object and from curvature variations of the object surfaces. Later, the contact, the perception can be used to change the tightening forces between the fingertips and object surface, or other parameters such as position and orientation of them. In the last years, sense of touch is being added to the sensing systems to a robotic manipulation stacks of both rigid and flexible objects, for example. For identification of objects, shape, texture, material, such as thickness, stiffness, to infer hardness from the chain of the object shape and contact forces, for detection of uncontrolled movements, such as slipping, to improve the quality of the grabs, for predictions of forces with which to grasp unknown objects. Our work more recent is inspired and motivated to find solutions in this last in the last two fields of these slides, this and this. So that robots can have a sense of touch, tactile sense must be interpreted in grip paths and robotic hands. The majority of the tactile sensing technologies are based on contact sensors. They can resistive, capacitive, piezoresistive, barometric, magnetics, optics. There are a lot of. You can find a review in this paper. In our work, we use 3 types of sensors. They are based on pressures, mapping with resistive technology, for example, TechScan, based on values from electrodes with barometric technology, for example, biotac sensors. This kind of the sensor provides a signal for each electrode. Based on camera with optical technology, for example, Digit by Facebook or GelSight by MIT. This provide as output an image. The barometric tactile sensors have a contact surface composed of a skin built with elastic material, which coats a conductive liquid. If we generate a contact, then the elastic skin deforms and produces a pressure on the liquid. These pressures affect to the electrodes. These electrodes are distributed under the skin, which record local data of the pressure. Also, an internal pressure sensors records global pressure data. This is located at the base of the fingertips. In these sensors, the output are signals. This is a collection of data sample in time. Each data is tactile reading. And the value of these readings are in this range between 0 and 35,000 approach, but depend on the sensor. In relation to optical sensors, its typical structure is composed of several layers, a contact surface. It is usually elastomer placed on metacrylate plate. The elastomer can be painted. Depending on the reflective and refractive properties, it is possible to observe geometrical chains of flexible materials. These geometrical chains are observed as contours and surface texture of contact objects. Moreover, if it has maker, we can observe the displacement and size change of the points. A camera composed of image sensor with a LED array. The camera capture image in which it is possible to observe the change of the property mentioned above. In these sensors, the output are image. These work lines are inspired by human ability to interact with everyday objects, although they are unknown. They have never been seen by the manipulator robot. As I mentioned, our work, more recent, is motivated to find solutions in two research lines for detections of uncontrolled movements, such as sleeping, to improve the quality of the graphs, and for prediction of forces with which to grasp unknown objects never seen before. Anyway, we need to compute the pre-grasping and initial grasping to obtain tactile information of objects. Therefore, for an initial grip of an object, we need to locate the object in the SN, but it doesn't need to be recognized, and also estimate areas or points where catch it. Our starting point is our vision-based grasp methods called geographs. Some features are it uses a three-dimensional point clouds. It compute graphs in 17 milliseconds. It only requires a single partial view of the objects, and it is completely object agnostic. It works on unknown objects. It can be adapted to different robots, hand morphologies. We have used with Allegro hand, Shadow hand, and Gripper to finger robotic and others. Our methods provides several points set, and it evaluates them with a coordinate metric that we propose to determine the beta grasping. It has limitations such as it requires a previous segmentation of the axon, the occlusion among objects, and the use of the single view limits the method. The method and some improvement were described in these two publications. Some limitations have been corrected in the last version by modifying the segmentation stage. The traditional clustering method to segment objects in the DSN was changed by deep learning techniques. Specifically, we use max recurrent convolutional neural networks, max region convolutional neural networks to perform locations in indoor and outdoor environments. This work was presented in a workshop of robotic manipulation in ICRA 2021. In another line, in relation to stability prediction, we have developed several methods. They use a single touch. This This is a single tactile symbol. We have designed them depending on the kind of sensor, but looking for a method can run with any touch sensors. Once the robot has picked up the object, we have worked on the application of tactile sensing for grasp assessment. This assessment is developed through the implementation of methods that allow us to detect and or predict how grip is stable or not stable. This method could be also included in a grasping controller. We have explored the implementation of two approaches using two different tactile sensors, BioTac SP, and more recently, we are using data recorded by the Digit sensor by Facebook, whereas BioTac records discrete signals from electrodes, and Digit provides tactile image as shown in figure. Therefore, we have created virtual representations of the signals, such as a virtual tactile image presented in a workshop of tactile precision in IROS 2018, and tactile graphs presented in another congress to be used as input of our method. More recently, we test the similar method, but in this case, we use Digit to do it. The first approach uses input data generated by 20 electrodes from 3 BioTac sensors, integrated and finger, thumb, index, and middle. We have tested some ways to convert electrode data into matrices. We have done this because we think that the electrodes should have similar pressure values in areas of fingertips close to each other. For example, this or this. For this reason, we have preferred to construct a virtual image, mapping the electrode values as pixels within a matrix. The pixels without a single electrode had to be filled. For example, this part with synthetic values, filled with synthetic values generated from its neighboring electrodes. Furthermore, we design a simple convolutional neural network to detect from the virtual tactile image if the graph is being stable or not. And we used different ways of organizing the image so that they could be processed by our neural model. For example, using horizontal chain, vertical chain, and stacking image are free channels. We prove different architectures of convolutional neural networks, and they were compared with traditional methods of machine learning, such as support, vector machine, random forest, and multilayer perception. In these traditional methods, the input were unidimensional signal from electrodes values instead of tactile image. In the second approach, we use as input data generated by 24 electrodes from 3 BioTac sensors again, but this time we created graphs to describe the dependence of influence of some electrodes on others with according to the proximity of closeness. The goal of graphs versus tactile image is to reflect the three-dimensional coordinates of the electrodes positions within sensor. By virtual tactile image or matrix, and they have only two-dimensional representations. We define 3 graphs, one for each finger tip. Each graph is a triplet, and it represents electrode positions mapped from physical coordinates, the connections among the electrodes according to the dependence, and the levels to be learned. The notation can be found in the slides. On the other hand, we have proved some different ways to connect the knobs or electrodes, where manually specified and direct connection following proximity and symmetric criteria. As a consequence, we redesigned the neural networks used for virtual images. Now the algorithm consists in a graph neural networks. In this way, we expected that the graph neural network was able to better capture the spatial locality and relationships of the tactile sensor reading, expressing them as graph instead of matrix. The results obtained with dataset composed of 51 objects shown in the table. On the figure, in this case, we did 5,500 graphs, employed a methodology of supervised learning. The grasping data for training and testing were recorded with different orientation of a shadow or a shadow hunt. The grasping points were chosen from our GeoGraph software. The experimentation consisting in grasping and lifting the object. In the object does not move or slip. The graphs were labeled as stable. The results comparing our two approaches, convolutional graph neural networks, shows that graph is a bit better than convolutional, considering an harmonic mean of precision and recall like F1 score. More recently, we are working with digit sensor, which were designed by Facebook. This optical sensor, we built 3-digit sensor. They have handcrafted constructions. Therefore, each of them provides different image. In the slides, we can observe two output image of contact with two different deformable objects, shoe, sole, and plastic apple. Due to the complexity of the feature extraction from each as by computer vision techniques, we have decided to use well-known models of deep convolutional networks. In particular, we have used as backbone of neural architecture free networks for classification from a state of art. In our experimentation, we use 9 different subjects, some deformable. The results show that the hit rates are high if we train and test with disjoint sets of data from same sensor, but the timing for a specific sensor cannot be used to test with other model. We need to build more digit units to generalize the method. Our goal is to avoid retrains the system if a sensor breaks and it has to be replaced with a new one. You can observe in this graph, for example, if you train one unit of the digit with one test, and afterwards you test with another kinds of the image from the another sensors. The score change a lot of, and you look for a new image from the new units of the sensors to generalize the method. Later, our detection system can be used to the control graphs. This work in Congress. You can use the union of the two prediction of the two fingertips, and afterwards, if some milliseconds the image don't show change, so you can plan you can plan the grasping and to do it. In this value, you can find these systems but running. On the other hand, we work in sleep prevision from tactile data. In this case, we have to use tactile sequence instead of a single touch. Recognizing the type of slabs, translational, rotational, and the displacement direction is more challenging than detecting only stability from one touch. We propose a learning methodology for detecting the direction of a sleep, 7 categories, using spatial temporal tactile features learned from biotac sensors. For example, these 4 directions, these and others, and this another possibility. The motion detection requires not only having a tactile measurements from current touch, but also a history of tactile measurements. How the figure shows. We propose 2 approaches based in recurrent neural networks that allow us to process both current touch and history of previous touches. The first approach uses the raw readings from values of 24 electrodes. The second approach uses virtual tactile images built from raw readings. We prove the performance of our approaches, changing number of layers, size of filters, number of filters, and etc. The results after training the networks 5 times, shuffling the training set. The training set is the basic set, and testing them each time with another kinds of the data sets to generalize the methods. In this case, our methods are tested with solid, small and textured objects. Can be seen in this figure. LSTM and convolutional STM are 2 architecture of neural networks, of recurrent networks that we use in these experimentations. The results are similar when the object is not small. For example, in this case and in this case. Therefore, it's not clear if virtual image is better than the raw readings in the experimentation, because you have used raw readings in this, and we have used the image in this and over. But if we analyze the standard deviation of results, convolutional recurrent network, and this is better because you reduce the standard deviation. The standard deviation is better. It's smaller than other. Furthermore, another conclusion is that rotational sleep is the most difficult movement to recognize. Seeing confusion matrix, sometimes there is a lot of confusion between the clockwise and anti-clockwise and the touch without sleeping. Finally, we research in tactile estimation to grasp known objects. The goal is to generate tactile data without contact. Human is able to grasp everyday objects, both rigid and deformable, without modeling forces. On occasion, researchers try to transfer the forces that the human used to manipulate an object for a robotic hands. Over time, researchers perform single touches on objects to learn to predict touch data. For example, to predict virtual tactile image from previous touches done with tactile sensor. Figure shows gel side sensor in this case. The results may not be applicable to robotic grip, but these ideas have served as a starting point for our research. Our purpose is to generate tactile responses that would be registered if a computer graph was carried out. This is done with two objectives. One is generate virtual tactile image, for example, to train tactile systems with learning and avoid making a lot of real graphs. This way we can create data sets for training with virtual grips. And another is to get a suboptimal starting grip. This is a stable grasping or grasping which allow us to reach stability easily. To do this, we use a three-dimensional representation of object to be graphs, specifically a point cloud captured from RGBD camera, estimation of grasping points to catch objects, as well as tactile data obtained from grips of other different objects. This information is used to teach a neural network. This work was presented in Transactions on Haptics and in a workshop of manipulation of deformable objects in IROS 2020. Our method consists in a semi-supervised regressions, generative adversarial and network neural architecture. The architecture of both networks is shown in the figure. We objectives not generate realistic samples of objects, but raw data that have similar features to those of the real samples. That is, the generator network does not create samples that match the real data distribution on the original space, but on the future space learned by discriminator network. The discriminator is based on well-known pointnet structure, which compute futures over three-dimensional points. Point cloud feature calculator generate a descriptor X with the 1024 futures using convolutions, and later we concatenate the grasping data such as contact points and pose hand, wrist orientation matrix. We use point clouds because this type of data structure represents the geometry of the object in a better way than a two-dimensional image, because it encodes curvature, volume, color, and among others. In order to produce a fake news, this is a synthetic point cloud. The architecture of the generator network is based on 3 layers of transposed convolutions. It receives as input a vector noise that has random value sample from an uniform distribution in order to generate a fake cloud. We selected an architecture that outputs cloud of 750 per 6 points. After experimenting with different sizes, we use a hyperbolic tangent activation function in the last layer of this network. It's important considering that the fake data are not labeled and they are not associated to tactile data. It represents unknown objects. They are used as part of training to achieve that. We execute graphs on 16 objects. 4 objects are deformable: staff minion, a flat ball, a sponge, volleyball. They were chosen because they have different shapes, textures, stiffness, and materials. For example, foams, synthetic fiber. 1,000 graphs samples were recorded for each object, and a sample of tactile reading registered by middle finger. Well, minion objects graphs can be shown in this figure. to create it and label samples, we omit the vector of tactile responses in our data set. We did several experiments changing the ratio of distribution between label and unlabeled samples. In the graph, we can observe the error of estimation of the global tactile data and local tactile data. This is the global and this is the local, the mean of the local, because we have 24 electrodes, but only one global pressure sensor. In our experimentation, we have changed the percentage of unlabeled samples used for training between 10% and 90%. The error is less than 8 approach in worst case. The main limitation is that two sensors do not provide exactly the same numeric values, nor they exhibit identical behavior. Moreover, the range of values are different from one sensor to another sensor. These limits the transferability of our models. Two objects with the same geometry can infer the same tactile responses due to limitations of the three-dimensional point cloud to encode features. This kind of the structure, our GAN is being integrated to predict if the proposal of contact points compute with other geographs method or with another. The idea is to provide stable graphs or not before it can be executed. The image shows samples about some objects, but modifying geographs for 3 fingers. GeoGraphs compute 3 points for graphs and architecture SRGAN method determine if the graphs will be stable or not before we do it. This way, achieve a best grasping because the initial position of graphs is suboptimal. So to finish, I would like to highlight that this work has been possible thanks to the funding of public resources from Spanish and European governments. Furthermore, I like to note that the work of these years would have been possible without the contributions and develops carried out by this team of people. Thanks for your attention and thanks to the organizers of this workshop. Thank you for the invitation.